At speeds exceeding Mach 5, a re-entering ballistic missile covers 5 kilometers every second. Atmospheric friction heats its nose cone to over 3,000 degrees Kelvin, and the entire defensive decision timeline shrinks to roughly 140 seconds. Tracking a high-speed ballistic missile from over 1,000 kilometers away is primarily a problem of Earth's geometry. India's ballistic missile defense architecture is engineered to counter a specific, dual-front threat calculus. The system must monitor launch sites capable of ranging the entire Indian subcontinent. To the north and east, China's arsenal includes the DF-26 Intermediate-Range Ballistic Missile. An intermediate-range ballistic missile, or IRBM, is a class of missile designed to strike targets between 3,000 and 5,500 kilometers away. On the Western Front, Pakistan deploys medium-range systems like the Shaheen-3, which can reach up to 2,750 kilometers. This 3D model shows the core physical constraint of tracking these launches, the curvature of the Earth. A ground-based radar cannot see through the planet's surface. Its line of sight is strictly bounded by the horizon. During its mid-course flight, the weapon remains physically hidden beneath that horizon. It only becomes visible to a sea-level radar when it drops below 80 kilometers in altitude, leaving very little time before impact. You cannot shoot down a hypersonic target by simply building a faster interceptor missile. Without a highly precise way to track the incoming threat through a cluttered atmosphere, an interceptor is essentially flying blind. National survival against this caliber of weaponry requires a completely integrated kill chain, a continuous loop of sensors, software, and kinetic weapons working in absolute synchronization. This diagram shows exactly why a ground-based radar cannot see a target 1,000 kilometers away. Radar waves travel in straight lines, so the Earth's physical curvature creates a geometric blind spot, blocking the line of sight to low-altitude launches. To bypass the horizon, the architecture relies on space-based infrared sensors to look down from orbit. As a missile launches, these satellites detect the massive aerothermal heating of its rocket plume, grabbing the very first coordinates of the threat. If you enjoyed deep dives into the physics and engineering of modern aerospace defense, take a second to like this video and subscribe to the channel. That initial space-based thermal detection is what wakes the rest of the defense network up, providing the crucial few minutes of lead time required to prepare a firing solution. As the incoming missile crests the geometric horizon, space sensors hand the tracking responsibility off to the heavy ground infrastructure. The primary eye of this layer is the Swordfish long-range tracking radar. Swordfish is an L-band active phased array system. L-band refers to a radio frequency between 1 and 2 GHz that travels long distances with very little atmospheric interference. A phased array means the antenna steers its radar beams electronically, tracking targets instantly without any rotating mechanical parts. This specific engineering allows the Swordfish to spot an object the size of a cricket ball from up to 800 kilometers away, simultaneously tracking up to 200 different targets traveling at Mach 12. Down at the tree line, defense architects face a distinct vulnerability. Long-range radars emit massive amounts of electromagnetic energy, broadcasting their static locations and making them highly visible targets for cheap, slow-moving kamikaze drones. To protect the primary sensors, the network deploys low-level surveillance radars like the Arudra and Ashwini, tuned specifically to detect drones with a low RCS. RCS means radar cross-section, which measures how visible an object is to radar waves. Every ping from the exosphere, the atmosphere, and the tree line funnels into a single software-intensive brain, the MCC. The MCC is the Mission Control Center, a central hub that processes the incoming data from the entire country. The computational burden is immense. 10 computers run in parallel to simultaneously filter out atmospheric noise, compute precise intercept geometries, and issue launch timings to the fire units in real time. The MCC's code acts as the engine of the entire network, taking passive early warning observations and turning them into an active, lethal kill chain. Look at this view of the Delhi-scape city. The theories of radar tracking are already operational realities here, with Phase 1 ballistic missile defense assets deployed specifically to protect the national capital region. This flowchart visualizes supercomputers processing telemetry. The software uses extended Kalman filters to lock chaotic, fragmented radar data into a stabilized flight trajectory. As this line hits the predicted impact zone, the system calculates kill probability and assigns the optimal interceptor battery. The Mission Control Center is the true intelligence of the shield. It translates disorganized electromagnetic echoes into a definitive battle plan. That battle plan is pushed to the Launch Control Center. Here, the computers calculate the split-second launch timing required to place an interceptor directly in the path of the incoming warhead. The first strike comes from the Prithvi Air Defense, or PAD, missile. This scale visualization shows the PAD missile executing an exo-atmospheric intercept. Exo-atmospheric means the physical collision occurs in the vacuum of space, destroying the target higher than 80 kilometers above the Earth's surface, before it can drop into its final, most dangerous terminal dive. If debris or a secondary warhead slips past that outer shield, the system immediately triggers the Advanced Air Defense, or AAD missile. The AAD is an endo-atmospheric interceptor. Endo-atmospheric means it engages targets lower down, entirely within the Earth's atmosphere, utilizing advanced aerodynamic fins to outmaneuver the incoming threat at altitudes below 30 kilometers. By stacking an outer space-based shield on top of an inner atmospheric shield, the architecture geometrically guarantees a kinetic impact, denying the incoming missile any uncontested path to the ground. India has repeatedly validated this Phase 1 network. Live-fire tests have proven the full sensor-to-shooter loop, resulting in direct hits on incoming test targets. But the baseline physics of warfare are shifting. Adversaries are fielding intercontinental ballistic missiles that launch from further away, and glide vehicles that maneuver unpredictably to evade standard radar tracking. To counter this, the Defense Research and Development Organization engineered Phase 2. At the center of this upgrade is the Very Long-Range Tracking Radar, or VLTR. This comparison visual shows how Phase 2 achieves its massive reach by replacing older imported hardware with domestic gallium nitride components, a highly efficient semiconductor material that handles intense heat and power. The indigenous L-band radar pushes its detection scan past 1,500 kilometers. That extended sensor envelope pairs directly with the upcoming AD-1 and AD-2 interceptors, which are being designed to reach out and destroy targets from 5,000 kilometers away. If you want to see exactly how these next-generation interceptors navigate at hypersonic speeds, hit the subscribe button and follow the channel for our upcoming engineering breakdowns. India's ballistic missile defense evolution demonstrates that strategic security cannot simply be bought off the shelf. It is achieved only by engineering the exact physics, software, and hardware of a completely sovereign kill chain. India's planned Phase 2 AD-1 and AD-2 interceptors are designed to engage these weapons in the exo-atmosphere. Calculating their intercept geometry requires immense lead time. To launch an interceptor in time to defeat an IRBM, the defense network must secure a stable track from at least 1,500 kilometers away. India's current Phase 1 early warning architecture relies on the Swordfish long-range tracking radar. This visualization of the radar range equation defines the core law of electromagnetic detection. Received power drops exponentially as distance increases. The limiting factor is the inverse fourth power of the range. Doubling a radar's detection distance demands 16 times the transmitted power. Traditional mechanically rotating radar dishes fail against Mach 12 threats. By the time a physical dish spins back around to complete a sweep, the target has already covered dozens of kilometers, breaking the tracking lock. Swordfish is an L-band system capable of tracking an object the size of a cricket ball at distances between 600 and 800 kilometers. The platform is an indigenous derivative of the Israeli Green Pine radar, utilizing Indian signal processing and power supplies. Extending this baseline capability to the 1,500-kilometer requirement of Phase 2 is not a matter of a simple software patch or turning up the dial on the current hardware. This animated diagram breaks down the radar equation. The critical variable is the denominator, range to the power of 4. Because the electromagnetic signal spreads out as it travels toward the target and spreads out again as the echo returns, the energy loss is exponential. Doubling a radar's detection range requires multiplying its transmit power by 16. Attempting to push conventional radar hardware to emit 16 times its normal power output causes catastrophic thermal failure. The internal components simply melt. Breaking the 1,500-kilometer threshold requires a shift in material science to handle the massive energy loads, rather than an incremental upgrade to existing systems. Long-range detection is only the first problem. The second is the extreme kinematics of the target itself. Hypersonic glide vehicles enter the atmosphere at speeds exceeding Mach 5. They maneuver laterally and vertically, generating a superheated plasma sheath fluctuating their radar cross-section. Traditional rotating dish radars fail against these targets. By the time a mechanical dish completes a full rotation to update its scan, a Mach 10 vehicle has deviated kilometers from its predicted flight path. This diagram illustrates an active electronically scanned array, or AESA, the architecture used by India's Phase 2 radars. An AESA is a radar technology where thousands of individual antenna elements emit and receive their own radio waves. Each element is controlled by a transmit-receive module. A transmit-receive module is a compact electronic circuit that manipulates the phase and amplitude of the radar signal locally at the antenna. By precisely shifting the timing of the signals across these thousands of modules, the radar steers its combined beam electronically at the speed of light without a single moving part. This enables a capability known as track-while-scan. The array can dedicate a fraction of its modules to update a high-precision track on a diving warhead every microsecond, while the rest of the modules continue scanning the horizon for new threats. AESA architecture eliminates mechanical latency, providing the microsecond update rates necessary to plot a hypersonic intercept. Even with electronic steering, projecting a beam past 1,500 kilometers still demands an immense amount of raw power at the array level. This split-screen diagram highlights the thermal limits of older designs. Legacy modules use gallium arsenide. Gallium arsenide is a semiconductor material historically used in radar electronics, which suffers from severe heat generation under heavy power loads. When packed tightly into an array, the system overheats before reaching the necessary power output. India's Phase 2 solution, engineered by DRDO's Electronics and Radar Development Establishment, replaces these components with gallium nitride. Gallium nitride is an advanced semiconductor material that conducts electrons far more efficiently than legacy materials, allowing it to operate at much higher voltages and temperatures. Gallium nitride delivers higher signal gain, wider bandwidth, and superior thermal dissipation. This material allows the new Very Long-Range Tracking Radar, or VLRTR, to handle the extreme power densities required for Phase 2 target detection. Prior to this development, India relied on imported Israeli and Russian platforms to achieve ranges over 1,000 kilometers. Domestic production of these arrays marks a transition to an independent hardware supply chain. The efficiency of gallium nitride allows the radar to punch through heavy atmospheric clutter and isolate the tiny radar cross-sections of maneuvering reentry vehicles at extreme distances. Without the specific thermal and electrical properties of gallium nitride, the raw power needed to satisfy the radar equation at 1,500 kilometers would literally melt the hardware. Raw sensor range is only half the equation. The data must be converted into a firing solution before the target crosses the intercept window. This flowchart outlines the Phase 2 data architecture. Radar measurements from distributed land and sea sensors flow continuously over low-latency networks into the Mission Control Center. The Mission Control Center is the central command facility that processes target telemetry to calculate the exact timing and geometry for an intercept. The MCC is the software core of the missile shield. It runs 10 concurrent computer systems to analyze the incoming data streams in real time. To generate a stable flight path from asynchronous radar pings, the MCC relies on extended Kalman filters. An extended Kalman filter is a mathematical algorithm that continuously updates the predicted position of a fast-moving target by smoothing out noisy and inaccurate sensor measurements. Once the filter outputs a definitive trajectory, the MCC assigns the target to a launch control center. The Launch Control Center is the facility responsible for the actual firing and mid-course guidance of the interceptor missile. The LCC computes the exact microsecond to fire the Phase 2 81 or 82 interceptors, sending them into the exo-atmosphere to meet the incoming warhead. Because the target maneuvers at hypersonic velocity, the firing solution degrades quickly. The MCC must continuously beam mid-course telemetry updates to the interceptor in flight. The kinetic interceptors carry the payload, but their accuracy is entirely dependent on the continuous, fused tracking data generated by the radar network and processed by the MCC. This map of the Indian subcontinent displays the VLRTR as the outermost layer of an integrated defense architecture. It operates in overlapping tiers. S-400 covers 400 kilometers, Project Kusha secures 600 kilometers, Phase 1 Swordfish extends to 800, and Phase 2 pushes past 1,500 kilometers. This later design ensures that as a ballistic target descends, it is tracked continuously across multiple frequency bands and engagement envelopes, minimizing blind spots. However, optimizing for high-altitude, high-speed targets introduces a different vulnerability. To achieve extreme range, VLRTR installations must emit massive amounts of electromagnetic energy. This makes their fixed geographical locations highly visible to adversaries conducting electronic intelligence gathering. These static, high-value arrays are prime targets for cheap, low-altitude kamikaze drones designed to overwhelm the site and blind the National Missile Defense Network. A 1,500-kilometer strategic shield remains viable only if its primary sensors are physically protected by localized point defense systems optimized to detect small, slow-moving threats. India's Phase 1 architecture is already mature and inducted. The indigenous GaN-powered Phase 2 radars and interceptors are moving through rigorous test cycles slated for operational deployment late in the decade. This deployment signals a transition from relying on foreign aerospace contractors to sustaining a fully independent defense engineering base. It is the physical realization of the self-reliant defense ecosystem set in motion decades ago by engineers like Dr. APJ Abdul Kalam. Hypersonic velocities make modern ballistic weapons difficult to track, but they are bound by the same physical laws as the sensors trying to stop them. By applying gallium nitride material science to active electronic arrays and fusing that data with predictive algorithms, India's defense architects are engineering a solution to the extreme mathematics of early warning detection. Below the exosphere lies the atmosphere, where the threat profile changes from ballistic trajectories to maneuverable cruise missiles and stealth fighter jets. Project Kusha cannot operate in isolation. It must physically and electronically overlap with existing disparate hardware, like the S-400, to ensure there are no blind spots in the radar coverage. If you found this breakdown of radar engineering helpful, hit the like button, subscribe to The Explainer, and tell us in the comments which defense architecture you want us to cover next. A common misconception in defense analysis is that X-band is the optimal choice for all missile defense radars. X-band is a high-frequency microwave band ranging from 8 to 12 GHz, known for narrow beams and high-resolution target discrimination. This split-screen model illustrates the penalty of high frequencies. Over extreme distances, X-band wavelengths suffer atmospheric absorption and rain fade, bleeding energy. India engineered the Swordfish for L-band, a lower frequency yielding longer wavelength that penetrate atmospheric clutter with minimal energy loss. This longer wavelength maximizes the power aperture gain product. It allows the radar to transmit massive amounts of energy over a vast volume of sky, guaranteeing early warning detection. High-resolution X-band is reserved for the terminal phase MFCR. An MFCR is a multifunction fire control radar deployed to protect highly specific localized geographies, like the National Capital Region. Selecting L-band for the primary long-range layer is a calculated physics trade-off, sacrificing localized terminal image resolution to guarantee the sheer geometric reach required for early warning. The technological baseline for this capability originated with the acquisition of 2 Israeli Green Pine radars in 2002 and 2005. To achieve sovereignty, DRDO replaced the imported core with indigenous hardware. DRDO is India's premier military research and development agency, and they successfully engineered domestic TR modules, digital controllers, and power conditioning units. The primary engineering bottleneck in these domestic active arrays is thermal management. Thousands of firing modules concentrate massive heat on the array face, which limits the radar's maximum radiated power and duty cycle. To break this limit for the Phase 2 VLRTR, engineers shifted from legacy gallium arsenide to GaN semiconductors. The VLRTR is the Very Long Range Tracking Radar, and GaN is gallium nitride, a highly resilient semiconductor material. GaN operates at higher voltages and extreme temperatures. It increases power efficiency and raw signal gain without expanding the physical footprint of the array. Mastering domestic GaN manufacturing allows DRDO to scale detection ranges beyond 1,500 kilometers without relying on foreign supply chains. The Swordfish VLRTR generates raw positional data that must be cleaned, fused, and actioned. The Mission Control Center, or MCC, acts as the brain of the architecture. The MCC is a software-intensive hub running parallel launch computers to process incoming sensor data. The network fuses asynchronous measurements from multiple distributed land and sea-based radars into a single, reliable 3D flight path. The mathematical solution relies on EKFs and predictive optimization models. An EKF is an extended Kalman filter, an algorithm that estimates a moving target's true state by smoothing out a stream of uncertain, noisy sensor measurements. This schematic traces the exact sequence. The MCC calculates the required number of interceptors, passes the filtered firing solution through a low-latency network to the Launch Control Center, and commands the strike. The BMD kill chain integrates sensors and low-latency software into a single network-centric system capable of processing data in real time. The kinetic result of the MCC's computation is the launch of an overlapping two-tier shield, comprising PAD and AAD interceptors. PAD is a high-altitude exo-atmospheric interceptor, while AAD is designed for lower-altitude endo-atmospheric engagements. Following launch, the VLRTR continues to generate mid-course target updates and transmits them directly to the interceptor in flight to adjust for sudden target maneuvers. Phase 2 of the program, projecting deployment by 2026 or 2027, scales this entire architecture to defeat 5,000-kilometer ICBM and MIRV threats. An ICBM is an intercontinental ballistic missile. A MIRV is a payload of multiple independent reentry warheads. This Phase 2 expansion relies on the newly unveiled, indigenous, GaN-based VLRTR, feeding data to the upcoming AD-1 and AD-2 hypersonic interceptors. By balancing the physics of L-band radio frequency propagation against the extreme kinematics of hypersonic flight, India has successfully engineered a sovereign, multi-layered shield. If you value this level of engineering breakdown, like this video, subscribe to Insight Engine, and let us know in the comments which defense architecture we should deconstruct next.